Well, good morning, folks. Small group so far this morning. That's okay. I'll talk to whoever's here. But before we jump into 6-2, is there anything you guys want to ask about or look at or had questions about? If not, let's go ahead and jump in. So we need essentially a question set that we want to talk about today. So how about how late are my friends? So let's say, you got a group of friends that when we're not all on lockdown, you can see. And, you've been, because you're just that kind of person, you've been tracking, when they're late and when they're not late. And, they all seem to be late a lot because people are late. And you have determined that their lateness has nothing to do with each other. So one person being late doesn't affect whether or not someone else is late. So they're not late because they're coming together or because they've coordinated this. The lateness is what we refer to as independent. One result doesn't affect the other results. So that's pivotal. And that no friend is really more likely to be late than any other. They're all just pretty late with the same probability, same basic probability. So those two restrictions, those two caveats are important for this tool we're going to talk about. Trials have to be independent. So the results of one trial can't affect another. If they do, then we have to use a different set of tools. And two, the probability for each trial has to be the same. So for trying to determine, whether friends are late or not, that's probably an oversimplification. We just wanted something to work on. But like we were talking last time about flipping a coin, your chances are, your probability of heads is 50%, probability of tails is 50%. And it doesn't matter what that coin has flipped before. It doesn't matter whether you're flipping it on a Tuesday or a Monday. The probability is always 50% heads, and the trials are always independent of each other. So there's a lot of things for which this is nicely qualified. The how many of my friends are going to be late is I don't know, probably oversimplified by this, but that's okay. So everyone's living on Hawaiian time. Yeah. Well, that's okay. And yeah, there are cultures out there where the idea of showing up on time is just crazy by comparison. So let's say you have, as I said, you've studied these friends long enough to know they're essentially independent of each other on whether they show up on time. And that probability of each one showing up on time is about the same. And you have determined the probability of on time to be about 60%. So go with 0.6. And you could do this using some of the probability tools we talked about in section 1, or just by collecting data. So, you mark down when they show up on time and when they don't. And after a while, you look at, okay, how often did they show up on time? And as a group, they generally showed up on time 60% of the time. So that's our probability of what we're going to call a success being on time. And the question we want to ask, say we have 3 friends showing up. And we want to know what is the probability or what is the likelihood? What is the probability? Oops. What? Can't write this morning. What is the probability that 2 will show up on time? Now, we talked a little bit yesterday about these binomial problems. This is a binomial distribution problem. We know it's a binomial distribution problem because our trials have only 2 results. They are either on time or they are not on time. And the variable we're studying isn't the yes or no, whether they're on time. The variable we are studying is how many successes we get, in this case, how many on times we get in a set number of trials. So here, of the 3 people coming over, we've got only a couple of possibilities. Either nobody shows up on time, 1 person shows up on time, 2 people show up on time, or all 3 of them show up on time. And essentially what we're looking for are those probabilities: the probability that we get no on time, probability that we get 1 on time, probability that we get 2 on time, probability that we get all 3 on time. So we specifically want to find the probability of 2 on time. Now we will, by the time we're done with this, be able to figure out the probability for any of those individually or even together. Find the probability that at least 2 are on time, or at most 1 is on time. So we'll be able to do all that kind of work as well. So before we go any farther, any questions on that setup? Any questions about the idea or the question that we're asking? Okay. So we want to compute this. So to do that, we're going to build some tools to speed all this up. But if we were going to do this purely by hand, the first thing that we'd want to build is what we call a sample space. Sample space is essentially a list of all the different things that could happen, so we could figure out, well, how many of them fit in these categories. So we've got 3 people coming over. 1, 2, 3. So how many different ways can we arrange those 3 people into successes or failures, on times or lates? Well, we certainly could have all 3 of them show up on time, so they could all be successes. It's probably not going to happen, but it could happen. So that's one of the things in our sample space. We could have the first person be on time, the second person be on time, and the third person be late. Or we could have the first person on time, last person on time, but the second one late. We could have the first one late, the other 2 on time. We could have the first 2 be late and the last one on time. We could have the first and the last one be late. We could have the last two be late. Or we could have them all be late. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8 possible scenarios. Does that seem reasonable so far? Now, again, you can imagine, as we talked about yesterday, that listing all of them out like this very quickly becomes an arduous amount of work. Figuring out how many possibilities there are is actually not that bad. For each trial, we have only 2 possibilities. So it's 2 possibilities times the next 2 possibilities times the third 2 possibilities. So it's just 2 times 2 times 2, or 2 to the third. That's our 8, our 1, 2, 3, 4, 5, 6, 7, 8 possibilities. But you can imagine if we had, say, 10 people showing up, 2 to the 10th, well, 2 to the 10th is a very large number. So writing out 2 to the 10th, I can't remember 2 to the 10th off the top of my head. I think it's 1024, but that's okay. Let's figure it out. I have a calculator over here somewhere. 2 to the 10th. Yeah, it's 1024. So if we had 10 people showing up, we'd have to write 10,024 different possibilities up, and that would be a pain in the neck. So we don't want to do that. So we'll need a way to speed this up of how many different ways we could arrange all those people. But for each one of these, we can figure out the probability of them occurring. So for a success, and a success, what's the probability of us getting a success? Well, 0.6. So 60% chance we'll have the first person be a success. And then we need the next person to be a success, so 0.6. And then we need the next person to be a success, so 0.6. And if we need this and that and this, what's the operation we use when we are anding our probabilities? Do we add them together or do we multiply them? Now, if we want to try adding them, 0.6 plus 0.6 plus 0.6 is 1.8. So that would be 180% probability. And we know that can't happen. You can't have a probability that's over 1. So remember, our ands sound like addition because what we're used to. But for probability, every and is a restriction. So this person has to show up late, and then this person has to show up late. So that makes it less likely. And when we multiply numbers less than 1 together, they get smaller. So in multiplying, we get smaller and smaller probabilities. About the same for mine too. So if we multiplied all those together, 0.6 times 0.6 times 0.6, or 0.6 to the third, to figure out what that is. We get about 0.216, so 0.216. So the probability of all 3 showing up on time is about 21%. So not very likely that they'll all show up on time. But that's okay. That actually even wasn't our question. Of the 3, we wanted to know the probability that 2 of them would show up on time. Well, 2 of them on time is this case, that case, and this case. And each of those cases are going to have 2 successes and 1 late, 1 failure. So again, our success is 60%. Our second success is 60%. Our failure, well, if our success is 60%, our failure has to be everything else. So we will often use the lowercase p for probability of success, so 0.6. And then for the probability of failure, we'll often use q. Your book likes to just put 1 minus p, and that's okay. So if our probability of success is 60%, our probability of failure would be the remaining 40%, right? So just 1 minus the 0.6, 0.4. So 2 successes and 1 late, or 2 successes and 1 failure, in any of its permutations, in any of its arrangements, is going to have 2 0.6s and 1.4, 2 successes and 1 failure. So it's going to have 2 P's and 1 Q. Now, how many different ways could we arrange that? Well, we had 3 different arrangements, so we could take this 2 successes and 1 failure and add it to itself 3 times, or since we know there are 3 of them, we could just multiply it by 3. 1 for that case, 1 for that case, 1 for that case. So 3 times 0.6 squared times 0.4 to the first. And we could calculate that. Take a moment, calculate that, and we'll see if we agree. Got a suggestion from Alan, 0.432. It's a fun number, 432. Anybody want to back him up or argue with him? Should come up with a problem about the probability of people giving an unsolicited response. But it might make me sad. I would agree if I did it right. You wouldn't agree if you didn't do it right? I would agree too. That's what I got, the 0.432. So we've actually got part of this filled out. We got 0.216, so about 21.6% chance that all 3 will show up. A 43.2% chance, or 0.432 proportion or probability of the time that exactly 2 of them will show up on time and the other one won't in any orientation. Could we figure out these other 2? So if we wanted the probability of 1 showing up, well, how many P's is that going to be? How many successes? That's going to be 1 success and 2 failures, right? And that 1 success and 2 failures has to be multiplied by the number of ways it could happen. So 1 success is 0.6, 2 failures, so q to the second power, 2 failures. And how many different ways can we have just 1 person show up on time? Well, that's 1 person showing up on time, that's 1 person showing up on time, and that's 1 person showing up on time. So again, there are 3 different ways those 2 times showing 2 times late, 1 time not late can be arranged. So probability of exactly 1 person showing up on time, we can calculate that too. 3 times 0.6 times 0.16 when we square that. And LAS, same thing I got. So 0.288. So about 28.8% chance that 1 person will show up late. Alan backs that up. Good. Now, if we wanted to finish out this chart, we have a couple options. We could do this again for no successes. So we'd have to figure out for P at 0, we'd have to figure out how many ways we can have no successes. And then P, well, no successes means P 0 times. And then if there's no P's, then they have to all be Q's. But if we look at how many different ways we got 0 successes, it only happened 1 possible way. So 1 times 0.6 to the 0. What is anything to the 0 power? Anything to the 0 power is nothing is a dangerous answer because it is nothing, but it's the multiplicative nothing. 0 is the additive nothing. It's what we add so that nothing happens. What we multiply such that nothing happens is a 1. So it turns into a 1. So anything to the 0 power, 1. And then 0.4 to the 3rd power, which is, well, I'll let you figure out what that is. Yeah, that often bothers people. Anything to the 0 power is 1. And I can give you a couple examples if you want. If we have, say, 2 to the 3rd, 2 to the 3rd is 8. 2 squared is 4. Notice we divide by 2 to get to that. 2 to the 1st, divide it by 2 again, you get 2. 2 to the 0. If we followed that pattern, half, half, that would have to be a 1. 2 to the negative 1 would be another half of that. 2 to the negative 2, another half of that. 2 to the negative 3, another half of that. So that might help, but lots of reasons. Stuff to the 0 power has to be 1. Anyway, what did you get for this value for the probability of no one showing up on time? Point 0.064, 0.064. Now, we also could have added these up and subtracted from 1. So 1 minus that sum, the 0.288 plus 0.432 plus 0.216, because we know these have to all add up to 1. So presumably that would have also given us about the 0.064. So either way would have been very reasonable. So before we abstract this a little bit more, questions where any of that came from. Like why we're raising those to those different powers. Why would we do the extra math if all we wanted to know was the... Oh, because we're going to want to be able to do this for anything. We're trying to learn a process here. All we wanted to know for this question was this particular one problem answer. But hey, we're here. Let's find everything else too, just to learn our process. Because all of a sudden, what's going to happen is that we're going to take these 3 friends and say, what if it is 10 friends? Oops. With still the p equal 0.6. With p equal 0.6. And we wanted to know, oops, what the likelihood was. What is the probability that, say, of these 10, how many do we want to show up on time? So what's the probability? Let's say exactly 7 will be on time. The nice thing is, for the most part, it's going to be exactly the same thing we did up here. The probability of 7 people showing up on time. It's going to be the number of ways that can happen. Number of ways we can arrange it. So up in the problem above, there were 3 different ways to arrange 2 successes, 3 different ways to arrange 1 success, 1 way to arrange 3 successes or all failures. So we'll have to figure out the number of ways that we can do that. But then times the number of successes, well, we need 7 successes. So the number of successes 7 times, and the number of failures the rest of the time, which in this case would be 3. So once we can figure out what this number is, it'll just be 0.6 to the 7th for the 7 successes, 0.4 to the 3rd for the 3 failures, These two should always add up to your number of trials. We just have to figure out how many different ways we can arrange 7 successes out of 10 trials. Now, up here, we just listed all 8 possibilities. But if you recall, for 10 friends, if we tried to do that, there would be 1,024 different possible arrangements. Of those 1,000 different possible arrangements, we'd have to find how many of them had 7 S's in them and count that all up. We're not going to do that. That is incredibly time-consuming and just asking for errors to be made. But we did talk about some tools for finding how many different ways we could arrange things. Remember when we were talking about factorial? So how did we do that? Well, you may remember we took the number of ways things could happen and its factorial. So here we have 10 boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 factorial for 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 for each box. Divide that by our n minus x factorial. That gets rid of all the extra boxes we don't need. And you might look back over that section where we talked about that. But because we want to consider, that would be how many different ways we could arrange all this stuff. But because we want to combine, we want to think of, say, this one where it's 2 S's and 1 L in that order. Oop. My screen went weird. You guys still see all that? Okay, I hit something weird on my machine here. So we wanted to figure out how many different ways we could arrange those 2 S's. So the order didn't matter. So we're going to take that tool we looked at the other day and divide by another little factorial to combine all the different ways we can write essentially the same thing out. Now, we could spend a fair amount of time talking about where this formula comes from. We talked a little bit about it the other day, but I don't want to get too bogged down in it. For this problem, our n is the 10. That's the number of trials we're going to run. X is the number of successes we want. So that's our 7. So if we want to know how many different ways we could arrange 7 things or 7 yeses in 10 spots where order doesn't matter, that's what this formula is going to do. Alan, the exclamation point is the factorial. We played with factorials a couple of days ago. You might look back at that tool. So, but what does the factorial do if we're going to write this out? That would be factorial is taking the number and multiplying everything less than that down to a 1. So it'd be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's us making those choices for the first piece of our trial. Then the 10 minus 7 is a 3 factorial. And the 7 factorial, so we're going to have 7 times 6 times 5 times 4 times 3 times 2 times 1. If we wanted to do this by hand, which in general we won't, by the way. And then 3 times 2 times 1. So that's our 10 factorial over 7 factorial. And then 10 minus 7, 3 factorial. And notice, just like the powers, these had to add up to be our 10. These two numbers should add up to make our 10. Again, we could multiply all this out. It's actually not that bad. The 7 through 1 here cancels with that 7 through 1. Let's see, the 3 could cancel with the 3 and the 9, leaving another 3. That 2 could cancel with the 2 and the 8, leaving a 4. The 1 doesn't matter, so that's going to be 120. So there are 120 different ways of the 1,024 different combinations. 120 of them have 7 successes and 3 failures. Now you can imagine that we're going to make a computer do this part, right? But it is nice to know we can do it by hand. And if you go good with your canceling, it's actually generally not that bad to do by hand. But yes, we're going to have computers do this for us. So if we want to define that probability of 7 people showing up on time, exactly, whatever 120 times 0.6 to the 7th power is times 0.4 to the 3rd power is going to give us that probability. And as I said, I'll show you a way to speed all this up in a little bit, but I do want to show you what's happening here. So let's calculate that real fast. Oops. And make sure we're all on the same page. That's what I got to, the 0.2, oops. I'm gonna go 1.5. So what's the probability that exactly 7 people will show up on time? Probability of exactly 7 people showing up on time is 21.5%. So if we tried to generalize this completely, if we wanted to find the probability of any particular outcome on n trials, so what's the probability that we have, 5 successes, 8 successes, 9 successes out of some number of trials, 15 trials, 10 trials, 100 trials, whatever it is? That probability can be computed with a combination of these two tools. The number of ways it could occur, we can always find with that n factorial over x factorial n minus x factorial. So it's a combinatorics tool. Combinatorics is the study of how things combine and permutate. It's a part of number theory. Your calculator has a symbol for it that it likes n combined r ways. It uses r instead of x. Sometimes you'll see books use it as n over r in parentheses like that, which is just weird, but it's a symbology that has grown up over the years. So this is a a pretty common tool from combinatorics for any of you who go into discrete mathematics or computer programming. But that number of ways it could happen, the number of ways it could be arranged, times the probability of success for every success, times the probability of failure for every failure, and that'll be what's left after we subtract all of our successes. So, for example, if for our situation here, we want to know the probability that exactly, let's say, 4 people show up on time out of our 10, again, we have to know how many trials, so probability of 4 of the 10. It would be just 10 factorial over, we want 4 successes, so 4 factorial. Everything else is the 6 factorial. How many different ways we could arrange everything? The 10 factorial, the 4 factorial, all the different ways we could arrange the 4 successes, the 6 factorial, how many different ways we could arrange the failures, all combined together. And then our probability of success was 0.6. How many times? Where we want 4 successes, so 4 times. Probability of failure was 0.4. We'd need that 6 times. I shouldn't have used 4s and 6s for both of these. This is 0.6 and 0.4 because of our probability of 60% and 40%. This 4 and 6 is our number of successes and number of failures. And we could grind a lot of that out kind of, by hand, like we've said, but you really literally can plug that into the calculator just as it is and get a result. Now, we will find a way to do it even faster than that, but let's start there. So 10, I showed you where the factorial button was the other day under the math menu. So math, probability number 4, so 10 factorial divided by the quantity 4 factorial times 6 factorial, 4 factorial times 6 factorial times the 0.6 to the 4th. So times the 0.6 to the 4th. Times the 0.4, times 0.4 to the 6th. Now, assuming that's all been typed in correctly, which frankly, yes, is a big assumption, that probability of 4 successes is about 11.1% or 0.111, I think it's 4. So we could just jot all that into the calculator and it'll crank it out. It is a little bit annoying to type in, but as I said, we're going to speed even that up. But questions about conceptually what's going on here? Where did everybody go? Has this been that horrible? Well, for those of you who are here, I've got a nice surprise for you, because the calculator has a way of doing really all of this for us. Because, Alan, you're right, it can be kind of a nightmare to try to calculate it all. So wouldn't it be nice if the calculator had a tool that just said, hey, if we could tell the calculator, I have a binomial problem with p equal to 0.6, n equal to 10, and x equal to 4, what is the probability? And the calculator would say, oh, it's this. That would be nice, right? Well, gosh, guess what it does? Just got to remember where it is. Right here above the variable button, above the button that says vars, there's a little blue word that says dist. I think it's dist. Or, what does it say? I cannot read that. It's supposed to be distribution. I say distribution like DITR or something like that. Mine's way too small. I can't see it. I'm old and blind. So if we go to that distribution button, second vars, we get to our distribution tools. We got normal PDF, normal CDF. We will use those later. Inverse normal, we'll use that later. Inverse T, we'll use that later. The chi-squared we won't use, but you'll use that in some of your other stats courses. But if you go down this list, you will find binomial. That's what we're looking at, binomial distributions. And there's two of them. There's binomial PDF and binomial CDF. We will use both of them. They do slightly different things. DISTR, distribution. Thank you, Alan. That was going to bug me until I found my calculator so I could read it. So we will need both of those, but the PDF's the one we're going to start with. So binomial PDF, the PDF stands for probability distribution function. And that's what we're doing. We're trying to find a value on the binomial probability distribution. So I want to grab that PDF tool. So I'm going to go up to that. It's number A. So we're going to go up to that, hit enter, and that's going to bring us to our menu. Now, depending on your calculator, you will either have this nice submenu where it asks you to put things in, or I think I'm going to move this so we can see that without it disappearing all the time, because that's irritating me. I think, Alan, your calculator was like this. The older calculators will just say binomial PDF and then have a parenthesis and be waiting for you to put in commands. So you've got to know what to type in, unfortunately. But the nice thing is the order is right here. It's always going to be binomial PDF and then trials, probability, number of successes. If you've got the nice menu up here, it makes it easier. So trials are 10, enter. Our probability of success, 0.6. Notice we don't have to tell it the probability of failure. It knows to subtract that from 1. Enter. X value, how many successes we want in our scenario. I want 4 successes in our scenario. Enter. And the paste will take that command and paste it to our home screen, and it will look like binomial PDF and then the NPX. So I think, Alan, you said your calculator was the older fashioned one. It'll just say binomial PDF, give you the parentheses, and then you just type in the 10.64. It's irritating because you have to know what order to put them in. So it's got to be in your notes somewhere. But the menu is nice. And if we've done this problem right, it should be 0.1114. 0.1114. does it really fast, really nicely. But to do that, we have to make sure we know what the N, the P, and the X stand for and what they do and what's happening. So it's going through and calculating all of these things, raising them all to the right powers, finding the combinations, and throwing us out that value. Is that less of a nightmare, Alan? Or Ali, is that less of a nightmare? So Nafar. So the nice thing about this is we could even do this with lots of trial. Let's say we have 120 friends coming over. Don't do that right now. You'll spread the virus, and so don't do that. So, and yeah, I don't even have 120. I wouldn't want them over if I had 120. Anyway, so say you had 120 quote unquote friends coming over, and they still had that probability of successfully showing up on time of 60%. And we wanted to know how likely exactly 78, why 78? I have no idea. How likely 78 exactly show up on time? Well, that's N of 120. Probability of success, still 0.6. How many successes do we want? 78. And we can just ask our shiny tool here. So again, second distribution, it's A, so it's binomial. By the way, you can just hit alpha A if you want to, but either way, we can get to that binomial PDF, probability distribution function. That's going to be what we're going to use when we want only one value. So enter. Trials were 120 this time. Our probability of success, still 0.6. The X value we want, how many successes we want, was 78. Paste that to our screen. Great. And we get about 4%. About a 4.03, why not, percent chance. Nice. Now let's make it bad for just a second. I got to ruin it before you go home, right? Go home like you're going anywhere. But before I let you go, now out of 120 friends, wanting to know what the likelihood that exactly 78 show up on time is like a very oddly specific question. Usually that's not what we want to know. We often want to know things like, how likely is it that at least this many people will show up on time? Say, to have your reservation honored at the venue for whatever party this is, you need at least 50 people to show up on time. So what's the probability that at least 50 show up on time? So at least 50 would be either 50 or 51 or 52 or 53 or and so on, all the way up to or all 120 show up on time, right? So we could, to answer this question, we could totally do this exact same process for 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63. all the way up to 120 and then add them together. Do you get the sense that's what we're going to do? No. Well, the nice thing is we don't have to, because we do have the other binomial tool here, that binomial CDF. And the binomial CDF is called the CDF, stands for cumulative distribution function. The problem with the CDF in terms of the question we have here is the CDF adds together the given value and everything lower than it. So if we used 50 in our binomial distribution and used 50, it would give us not what we want, these bigger numbers. It would give us the 50 and the 49 and the 48 and the 47 all the way down to 0. We don't want that. So what do? If we want the probability of being greater than or equal to 50, this is often how we'll see that written, the probability that our X, our number of successes, is greater than or equal to 50, our cumulative function doesn't do greater than, it does less than. So what we'll do is we'll take the probability of being less than or equal to 49, because our cumulative distribution function does that, and subtract that from 1. And this is going to be common with a lot of our tools. A lot of our tools by default go from a given value downward. If we don't want the downward values, we want the upward values, we do this. We find the complement. Talked about that before. Find everything, to find everything above, find everything below, subtract from 1. That makes sense? We've got to use the 49 because I want the 50 to be in my upper set. So essentially we're trying to get rid of 49 and down by subtracting it off. So we're going to go to our binomial distribution function, but this time use CDF, still with the 120 trials, still with the probability of success of 0.6, but this time with the 49 and the CDF is going to give us 49 and below. So, oh, I don't want that, sorry. So go to our distribution. This time go to binomial CDF because we want it to accumulate. We want to add together all those things. So cumulative distribution function, still 120 trials, still a probability of success of 0.6. But again, this time we want 49 and down. The and down comes from the CDF. So that gave us a very tiny number. The 1.7 doesn't look that tiny, but that e to the -5, remember that's scientific notation, right? It means we got to move that decimal place over 5 spots. So this turned into 1 minus 0.0000017. Out of 120 people, 60% chance that they will show up on time, having only 49 people show up on time or less, really unlikely. Subtract those, and we will get 0.9999, but 83. So what's the probability that we will have at least 50 people show up on time? Really high, 99.998% chance that at least 50% will show up on time. Now, calculating all of that by hand would have been super, super irritating. But if we know how to use those calculator tools, and Excel has similar tools, and we'll use those as well. It has exactly the same tools. They're just labeled a little bit differently for the Excel commands instead of the calculator commands. But yeah, allows us to compute these things very quickly. Does the same stuff in the background, figures out that whole factorial formula, multiplies by the probability of success, the success times, the failure times, and adds them all together. It does all that in the background, but we don't have to. Percentage shows 50 or more people will show up on time. Yes. Almost 100% probable. I mean, that's virtually guaranteed to have happen. Now, a couple questions that should naturally come out of this are things like, well, how many people, how many friends here do we expect to show up on time? Well, remember expected value? We talked about expected value in 6.1. Expected value was a mean, right? So this question is technically asking, what is the mean of this distribution? On average, how many people are going to show up? What's the mean? Well, if 60% of them show up on time and there's 120 of them, does 120 times the 60% seem reasonable? 60% of the 120? If there's a 60% chance each person shows up on time, then 60% of those people should show up on time, which is going to be what, 72 people. So on average, 72 people would show up on time. So at least 50? Yeah, at least 50. We'd expect that to happen almost always. This even turns into a formula for us, frankly. The mean, the average, number of trials times the probability of success. If 60% of them should show up on time, then that 60% of them, multiply them together, gives you how many successes you have. Very last thing before I let you go, the one dangerous part here is this mean is not X bar. You remember X bar was the symbol we used for a mean, but that was a mean for a sample. This isn't a sample. A probability distribution is every possible thing that could happen. So a probability distribution is a population. So this average isn't the average of a sample. It's not a descriptive statistics. It is the average of the entire population of things that could ever occur. So instead of using the sample symbol for mean, we have to use the population mean. So that is the Greek letter mu. Kind of looks like a U with a little funny long thing on the front. And that is our population mean, where X bar was our sample mean. In general, we use Roman letters for samples, Greek letters for populations, or for parameters, if you prefer. So that's got to be a Greek mu. Questions about that? So if you're asked for an expected value, weighted average, mean for a probability distribution, for a binomial distribution, just NP. How many people do you expect to show up? 60% of them. Okay, so fine, 60% of them. Cool. Your book will also talk about sigma. Sigma is the Greek S, so that's for standard deviation. If you want a standard deviation, remember standard deviations when we calculated them had a big square root in them. These will also have a square root, but it's just NPQ. So multiply the n times the probability of success times the probability of failure, take that thing's square root, gives you a standard deviation. I don't want to go into where that formula comes from. It's actually kind of a calculus, complicated answer. But if anybody ever asks you for the standard deviation of a binomial distribution, that's how we find it. How would we use it? Well, what is the square root of 120 times 0.6 times 0.4? I don't know. We'll go find out. Square root of 120 times 0.6 times 0.4 equals 5 point, I'm going to say 5.4. 5.4. So that's our standard deviation. That's our mean. They're both in people. So on average, we'd expect 72 people to show up on time. Typically, we'd get that 72 plus or minus 5.4. Remember, unusual, it would be unusual to be 2 standard deviations from the mean. Oops, well, 5.4. So it would be unusual to be plus or minus 2 of those out. So 72 plus or minus, was that 10.8? So we would usually expect to be anywhere between 82.8 people on the high end showing up on time, and what would that be? 61.2 people showing up on the low end. 95% of the time, that's all good old empirical rule, 95% of the time between 61 and 82 people will show up on time. So it's the same interpretation of your standard deviation as before. It just has a nice little formula based on the probabilities. So read that in your text, play with that a bit. If any questions come out of that, let me know. But that is our just old interpretation of standard deviation and mean. They're just super easy to find in binomial scenarios because the formulas are really nice. Well, that's our time today. Any questions on that? So, as I normally do, I do like to show you guys where some of this stuff comes from. You know, I'm hand waving a little bit over this combinatorics formula and this standard deviation formula, and I think that's probably in our best interests to not go deep into where those come from. But I do want you guys have a sense of where these tools come from and how they work. But the nice thing with the calculator, CDF, and PDF functions, we can calculate these things nice and fast. Cool. All right. Have a wonderful day. I'll see you. Today is Thursday, right? So I'll see you guys on Monday. If any questions come up between now and Monday, let me know. Have a wonderful day. I will. Thank you. You too.